Reactive Chemistry Depth Study by William Prentice. Questioning and predicting. Inquiry question, aim, and hypothesis. Inquiry question. What is the maximum voltage that different types of batteries can emit at room temperature? Aim. To verify Nernst's law that cell potential voltage is inversely proportional to the natural log of the molar ratio between the concentration of the anode and the cathode. Hypothesis. If Nernst's law is true, then the reaction quotient and cell potential are logarithmically related. When 0 equals the natural log of Q, then Q equals 1, demonstrating when the reaction quotient equals 0, the voltage produced will be its maximum, thus demonstrating that the maximum voltage of a battery is its standard potential voltage. Knowledge and understanding, communicating, introduction and background theory of rapport. Background information supporting the hypothesis. Nernst's law is derived from three equations. 1, delta G is equal to negative Fe. 2, delta G standard is equal to negative E, Fe standard. 3, delta G is equal to delta G standard plus RT ln Q. The first equation can be explained by mathematical intuition. The equation basically states that the energy released is equal to the number of electrons measured in moles, multiplied by Faraday's constant, which is the charge of 1 mole of electrons, which is then further multiplied by the voltage given off by the redox reaction. This is measured in volts, or equivalently joules per coulomb. Mathematically, the equation of the units is moles times coulomb per moles times joules per coulomb. So the moles and the coulombs cancel out. So you have your change in energy release. So mathematically, this equation makes sense. The second equation is nearly identical to the first, only this time the equation isn't in terms of voltage, but instead is in terms of standard potential voltage. I'll discuss what makes a voltage standard potential later in the knowledge and understanding section. The third equation relates to thermodynamics and the change of Gibbs-Free's energy, which is the change of Gibbs-Free energy is equal to the standard potential Gibbs-Free energy plus the product of the ideal gas constant and the temperature and the natural log of the reaction quotient. Anyway, using these three equations, Nernst's law can be proven mathematically. Step 1. Sub this value into delta G, and this value into delta G0. So then you get negative NFE is equal to negative NFE0 plus RT ln Q. From there, we do some simple division. Divide by NF throughout the whole equation. And voila, there is Nernst's law. Now, if you want to make this equation specific to room temperature, all you have to do is sub in the ideal gas constant, R, which is 8.314 joules per mole Kelvin, and the temperature, which is 297.15 Kelvin, and Faraday's constant, which is about 96,485. After subbing all these values, what do you get? This equation below. And this equation is both useful in the hypothesis discussed before and for the verification of the results later. Foundations of a galvanic cell. I'll be talking about redox reactions, metal precipitation reactions, metal reactivity, oxidization and reduction, a description of a galvanic cell, standard electropotential, calculating voltages, and the link between standard electropotential and reactivity of metals. So redox reaction. A redox reaction is any chemical reaction that involves the transference of electrons. Redox is the words reduction and oxidization shoved into one, and hence we get the word redox. The most common form of a redox reaction is a metal precipitation reaction. A metal precipitation reaction occurs when a solid metal reacts with an aqueous salt. For such a reaction to take place, the salt metal must be more reactive than the metal ion in solution. Atomically, this is because metals of high reactivity are more willing to lose electrons. The loss of electrons from the more reactive solid metal makes it become a cation, and the original metal cation will gain those electrons, causing it to become a solid precipitate. Metal reactivity. So what impacts metal reactivity? Most strength of an element relates to its electron configuration. The most reactive metals are generally have one outer electron and multiple energy levels. This is because, 1, with one outer electron present in the configuration, the atomic radius increases. This increase occurs due to the lack of protons and electrons present in the nucleus compared to other elements. This results in a low electrostatic force within the nucleus, thus allowing the valence electrons to be further from the nucleus, bringing an increase in atomic radius. Moreover, when an element has a lot of energy levels, the shielding or screening effect will occur, which in turn increases the radius. The shielding effect is the decrease in electrostatic force between a nucleus and an outermost electron brought by the completely filled electron shells between the nucleus and the outermost electron. So using this knowledge, a metal with a valency of 1 will have a large atomic radius, and the energy required to attract an electron and break the electrostatic force within the nucleus would be very weak. In other words, the atom would have a low first ionization level. Easier transfer of electrons, the more reactive the metal. So in summary, what makes a metal reactive? It all stems from the electron configuration, which affects the atomic radius, electrostatic forces in the nucleus, and the first ionization level, and overall, the reactivity of a metal. Reduction and oxidization. In redox reactions, several equations can be derived, such as redox, full ionic, and net ionic equations. A redox reaction is the simple reaction equation of reactants produces products. However, from this reaction, you can derive the ionic interactions within the reaction. To demonstrate this, let us use an example. Aqueous silver chloride plus solid sodium produces aqueous sodium chloride plus silver solid. This is a redox reaction. The full ionic equation would be solid sodium plus aqueous silver ion plus aqueous chloride ion produces aqueous sodium ion plus aqueous chloride ion plus solid silver. And the net ionic equation would be solid sodium plus aqueous silver ion produces aqueous sodium ion plus solid silver. I'll explain how I derive these equations, but from the meanwhile, let's just continue. So anyway, from these equations, two half equations can be formed. A half equation is two different equations that either describes the receiving or donating of electrons, as seen with silver ions receiving electrons and sodium donating electrons. These two half equations have categories, reduction and oxidization. Reduction ironically means to gain electrons, and oxidization, although nothing to do with oxygen, means to lose electrons. Anyway, a good way to remember this is oil rig. Oxidation is loss, reduction is gain. Oxidation number rules. To determine what charge an ion has within a salt solution, scientists have come up with something called oxidation numbers. The oxidation number of an element in a molecule or ion is the charge the atom of the element would carry if it were completely ionic. Here are the rules. For your full understanding and development of the rules, please pause the video. So if you guys pause the video, I'm back and we're doing reduction and oxidization part 2. So using the knowledge that we've gained from the previous slide, let's see how from the redox equation we got the full ionic and net ionic equation. So redox is full ionic. So as you can see with sodium has a charge of 0 for both equations. This is because elemental states have an oxidization number of 0. And then if we look at chlorine and our rules, chlorine would have an oxidation number of -1. And since this whole compound is 0, we want silver to be +1. Oh, don't mind the messing drawing. So that's where we get +1 silver, -1 chlorine. And then we just use the same logic for sodium chloride and silver. And that's where we get that. And then it's quite simple where we get the full ionic to the net ionic. We just take out the spectre ions. And what would that be? That would be the chlorine ion here, and here it does nothing, so we don't want it. And that's our net ionic. We just remove that, and voila. And then how do we get our oxidization number? Well, we use oil ring, and oxidization is loss. So sodium is losing an electron. So we start off with sodium here, and since it's losing an electron, it's losing negativity, so it actually becomes positive, and the electron's free. Where we got, and then the other hand of it, other side is reduction. So we got reduction is gain. So we got the silver ion gains the electron, and the minus and the plus they counterbalance, and you just get a neutral silver. And because elemental states have an oxidization number of 0, that's why silver becomes solid, and that's the equations explained. So how do galvanic cells work? Here is a galvanic cell. A galvanic cell is a device that converts chemical energy into electrical energy. In this device, we have our electrodes or half cells separated by a salt bridge. The two electrodes are then attached by a conductive wire passing through an electronic device. For this galvanic cell, its redox reactions are split into two separate half equations. So we have for anode, we have our oxidization reaction, which is zinc becomes a zinc positive 2 ion with the loss of 2 electrons. And then you got reduction here with the copper ion actually gaining 2 electrons to form solid copper. So this is how let's say the electron's journey. So it reacts, zinc here will react with the zinc sulfate, the half reaction. So it's going to actually form more zinc. It's going to form some ions off the zinc. Whilst it does that, 2 electrons are released, and they go up through here, through the wire, through the electronic device so we can do work, or the voltmeter, and we go down here to copper, we go down, until the charges meet of the copper ion and the electrons, and the copper ion actually gets attracted to electrons and actually forms a solid copper, as seen in the half reaction, and that'll form a metal precipitation on the actual metal electrode. So that's the actual electron's journey. But now we have to explain what's the purpose of the salt bridge. The first reason is quite simple. It just allows there to be a complete electronic circuit, so the electrons can go through, back, and then back up, kind of. And I'm just going to delete that so I have more room for what I have to say for the second reason, and we might use a different colour, blue. Okay, so we got our salt bridge. Another reason is a bit more complex, but I'm sure all you chemists can understand it. So we have our zinc right here, and as we discussed, that zinc will become zinc 2 ions, and over time it's going to build up and build up until it's overly positive here. This will become positive charge, and the opposite will happen here. So this will go away, and this will be losing these ions, and this will grow and precipitate, and this will become negative. Now the salt bridge, its job is to counterbalance those charges. So it's positive here. This actual nitrate ion will get attracted to the positive zinc ions and come down through here, and actually get attracted to the zinc, allowing for this positive charge to no longer be positive but just be neutral. And it's the same with the potassium. Over here, we go down, and that will counterbalance with the too much sulfate ions, and they'll keep it not negative but just neutral. Also, a huge, but always, to my perceptions, that's clearly missed in salt bridges, is actually the actual substance that's used in salt bridge. Now, you want to pick the right substance that's used in a salt bridge because you don't want to form precipitate. If we use our solubility rules that we've learned in the past, we should know whether or not this will form a precipitate. So all nitrates are soluble, so we're good here, and all first group metals are soluble too. So we're all good here for this salt bridge, but we always have to be careful what elements you place in the salt bridge because you want it to be soluble. So to finish off, when will a galvanic cell stop producing electricity? Two major ways in a galvanic cell will stop producing electricity is first that the salt bridge is faulty or it's removed from the circuit or the wire is removed, but also when this zinc actually erodes as it produces the zinc ions. So this will soon erode above the solution, and when it does that, the current is broken and the galvanic cell stops working. So that's just a basic rundown of how a galvanic cell works. Standard electrode potential. A standard electrode potential is the voltage emitted by an elemental atom and neutral charged molecules reducing relative to hydrogen under the following conditions. These conditions are 298.15 Kelvin, or room temperature, 103.25 kilopascals, or pressure at room temperature, and 1 molarity of solutions for both electrodes. Thus, the point of reference of standard electrode potential is hydrogen. So hydrogen has 0 volts for its standard electrode potential. As you can see from the table, when the standard potential is positive, an element is more likely to be reduced rather than being oxidized. Calculating voltage. Calculating voltage for a standard electrode is quite simple. All it is the sum of the standard voltage of reduction half equation plus the standard voltage of oxidation half equation. For example, if you do 2 half equations of zinc and copper, copper is reducing and has a standard reduction potential of plus 0.34. For zinc is oxidizing and has a standard reduction potential of negative 0.76. But since it is oxidizing rather than reducing, that 0.76 becomes actually positive 0.76. And we apply to the formula. The standard voltage is 0.34 plus 0.76, which is equal to 1.1. Therefore, a galvanic cell of copper and zinc under standard conditions is 1.1 volts. Standard electrode potential and reactivity of metals. The difference between standard electrode potential and reactivity of metals is the lower the standard electrode potential, the more reactive the metal. This is because of 2 reasons. Reason 1, the reactivity of a metal measures how easily a metal atom can lose electrons. The standard electrode potential measures also the likelihood of an atom reducing. Hence, if that figure gets lower, even negative, its likelihood of oxidization is very high. Oxidization, as stated before, is the loss of electrons. Thus, a link can be made if a metal is good at oxidization, it is very reactive, and hence the trends of lower standard electrode potential and higher reactivity can be explained. The second reason is the mathematical proof of such trend. Here are some half equations below from the standard electrode potential table. We know that aluminium has a standard voltage of negative 1.66 volts, and magnesium has a standard voltage of minus 2.37 volts. From these half equations, you can derive the net ionic equation, which is here below. From observations, the magnesium becomes an ion and displaces the aluminium. Therefore, magnesium is more reactive than aluminium, and the same trend still exists. The lower the standard electropotential, the more reactive the metal. Planning and conducting investigations. Risk assessment, equipment list, and method. Risk assessment part 1. Please pause the video to ensure that you have read all content. Risk assessment part 2. Please pause the video to ensure that you have read all content. Here is the equipment list and variable list. Please pause video to ensure you have read all content. Here is method part 1. Please pause video to ensure that you have read all content. Here is method part 2. Please pause video to ensure you have read all content. Here's method part 3. Please pause video to ensure that you have read all content. Processing and analyzing data. Table, graph, and discussion. The effect of reaction quotient on voltage. Table 1. The effect of the reaction quotient on voltage. Graph 1. Discussion. Analysis of results and trends of data from first-hand investigation. The results from the first-hand investigation prove that there is a logarithmic relationship with the reaction quotient and voltage. There is an inverse logarithmic function caused by the two variables. This means as reaction quotient decreases, the voltage produced increases logarithmically. Mathematically, it looks like y equals negative h ln x plus k, where y equals the dependent variable, voltage, and x equals the independent variable, the reaction quotient, and h and k are two different constants. Through the aid of the digital technology Excel, the equation of the function is y equals negative 0.096 ln x plus 1.0964. So the equation really looks like E equals negative 0.096 ln q plus 10964. If we refer back to Nernst's law, which is E equals EO minus 0.025 on n times ln q at room temperature, then the negative constant in front of ln q should be equal to the coefficient to 0.025 on n. So from the equation obtained, the front constant of ln q is minus 0.096 given from Excel. For the Nernst equation, the constant in front of ln q is 0.025 on n. However, we know n is 2, as 2 electrons are oxidized from zinc. So the coefficient becomes negative 0.0257 on 2, which is negative 0.012. Therefore, the constants are in close proximity with each other, with plus minus 0.08315 difference. Moreover, the constant 1.096 should approximately equal the standard potential. The standard potential of zinc and copper equals 1.1. Thus, the values are in close proximity with each other, with a difference of plus minus 0.0036. Therefore, the results and trends from the first-hand investigation have verified the logarithmic relationship that exists between the electrical potential and the reaction quotient. In addition to that, the results and trends have also verified the coefficients and constants that exist in Nernst's equation. Discussion. Assesses the accuracy and validity of findings from the first-hand investigation. Validity. The findings from the first-hand investigation were very valid. This is because all control variables were controlled, such as the type of voltmeter used, type of wire, length of wire, thickness of wire, same electrodes, same electrolyte solution, same volume of electrolytes, same solution in salt bridge, same concentration of solution in salt bridge, same overall temperature in the system, and same overall pressure in the system. The results were also valid as it tested the hypothesis and answered the inquiry question. The method allowed for the results to give a clear answer to the inquiry question by testing a range of reaction quotients, which were 10,000, 1,000, 100, 10, and 1, thus making it valid. Moreover, the method also allowed for the hypothesis to be proven or disproven by using quantitative dependent and independent variables. Therefore, the findings from the first-hand investigation are highly valid. Accuracy. The findings from the first-hand investigation were highly accurate. This is because although the voltmetric glass, the 10 millimeter pipette and beaker had inaccuracies of plus minus 0.2% and plus minus 0.2% and 5% plus minus 5% respectively, the accuracy of the procedure outweighs such weaknesses. The accurate procedure entails the correct usage, selection, and calibration of measuring equipment. Also the reality that the measured volumes in the beaker did not require to be accurate, and no avoidable systematic and random error was present. Hence, the results are highly accurate. Problem solving. Justifications of modifications. My modifications are size, the type of barrier, physical properties of electrolytes, and the internal circuit design. So justification of size. Size would need to be modified for my experimental galvanic design to be suitable for the use in an electronic device such as a TV remote. This is because devices such as TV remotes are small and hence require small batteries or galvanic cells. Moreover, another reason for reducing the size is product-wise. The smaller the galvanic cell, the less equipment is needed to build it. And the less equipment needed, the less money spent on producing the galvanic cell. Reason 3, for everyday consumers, they want their products to be convenient. By reducing the size of a galvanic cell, size won't inconvenience them, but instead the battery will be portable, thus making it very convenient. Hence, this design is very applicable to the real world. Justification of the type of barrier. The type of barrier used would need to be modified for my experimental galvanic cell design to be suitable for use in an electronic device such as a TV remote. A better alternative to a salt bridge is a porous disc. The advantages of a salt bridge are as follows. It completes an electrical current and counterbalances charges. The disadvantages for a salt bridge are it takes up a large space and it's very fragile. However, the porous disc has the exact same advantages except that it's non-fragile and is compact. Therefore, logically, it can be argued that the advantages of a porous disc outweigh the advantages of a salt bridge. But why does this make a salt bridge more suitable? Why does this make a porous disc more suitable than a salt bridge in an electronic device? 2 reasons. Reason 1 is safety. Porous disc makes batteries safer compared to if it was used with a salt bridge. This is because with a porous disc, you can remove any risk of broken glassware and hence making it clearly applicable to the real world. Reason 2 is reliability. Since the porous disc is less likely to break than the salt bridge due to its non-fragile nature, then when it's used in TV remotes, it'll be less likely to break and less likely to be faulty. Therefore, again, making it very applicable to the real world. Alright, justification of physical properties of electrodes. The type of physical properties associated with electrodes will need to be modified for my experimental galvanic cell design to be suitable for the use in an electronic device such as a TV remote. A better alternative to a liquid electrolyte is a gel electrolyte. This is because gels have a higher viscosity than liquid, making it more compact and preventing, due to spillage, a change like half cells coming into contact with each other. This will make a battery for a TV remote more reliable and efficient, and hence make it more applicable to the real world. And last but not least, the circuit design. Justification for the circuit design. The internal circuit design will need to be modified for my experimental galvanic cell to be suitable for use in an electronic device such as a TV remote. The current electronic The current electronic current in my experimental galvanic cell is conductive wires being attached to the anode, then attached to an electronic device, back to the anode, and then the electrons travel through the salt bridge, and the circuit is complete. However, better alternative to this would to have a conductive material in between two galvanic cells, where it would obtain electrons from the negative terminal and transport it to the positive terminal. This electrical current design allows for a compact and more convenient battery compared to the original galvanic cell design. This is because the new design eliminates the use of wires and eliminates the taking up of space. Thus, logically, the internal circuit design would need to be modified for the conveniency and efficiency of a battery, therefore making this new galvanic cell design very applicable to the real world. Bibliography.